When you look at the turbulent surface of the ocean, you are watching a system defined by continuous change. The physical world is rarely static. It is governed by constantly shifting variables that dictate how heat flows, how structures bend, and how fluids move. To describe these flowing systems, mathematicians use differential equations. A differential equation is a mathematical statement that relates a function with its derivatives, essentially describing how something changes over time or space. While powerful, these equations rarely provide a single definitive answer on their own. Take a simple example, an equation stating that a function's rate of change is equal to the function itself. The solution is a one-parameter family, written as y equals c times e to the power of x. That letter c is a constant, and in a general sense, it can be any real number. Because c is undefined, this single equation generates an infinite family of curves. We are left with unlimited answers, each one mapping out a different path across the graph. In theoretical math, infinite possibilities are a curiosity. In engineering, they are a problem. If you are trying to track a rocket's trajectory or predict a circuit's voltage, you cannot rely on an infinite set of options. You need one exact, perfectly reliable answer. To find that specific answer, we provide the equation with a known starting point, an initial condition. Imagine taking our field of endless curves and defining a physical reality. We state that at time 0, our value is exactly 3. That pin filters out the noise. By locking in our starting coordinates, every other trajectory vanishes, leaving a single perfectly defined curve. This pairing, a differential equation and a starting point, is called an initial value problem, or IVP. An IVP is a differential equation paired with a specific value of the unknown function at a given point in its domain. This chart compares the formal notation for these setups. We can create a first-order problem by pinning down a starting position, or a second-order problem by anchoring both the starting position and the initial slope of the trajectory. The initial condition acts as a physical anchor. It takes a theoretical equation of infinite possibilities and forces it to describe one specific trajectory in the real world. But is this system always reliable? Does dropping a pin guarantee that we will find exactly one path forward? This image presents the two criteria every initial value problem must face. First, we must ask if a solution actually exists. Second, if it does, is that solution unique? Sometimes the math breaks. You can drop your initial condition pin, but the equation yields no valid solutions. Your starting point is mathematically isolated, and there is no path forward. Example 2 on this slide shows a different issue. Here, the initial condition is valid, but the math branches into two contradictory paths that both cross through our starting pin. In applied science, multiple answers are just as problematic as zero answers. Without strict mathematical safeguards, an initial value problem can easily lead to dangerous dead ends or unpredictable branching paths. To navigate these issues, mathematicians rely on the existence and uniqueness theorem. It is the definitive safeguard against mathematical unpredictability. To see how this works, we view it spatially. We start with our initial condition, the dropped pin, sitting on the coordinate plane. The theorem requires us to establish a safe zone around this point. We draw a rectangular boundary, creating a defined region of space called R. The theorem then performs its first scan, checking if the function is continuous inside the box, looking for a landscape free of holes or jumps. Next, it performs a stricter scan by calculating the partial derivative with respect to y. A partial derivative measures how a function changes as one variable varies while all others are held constant. This scan ensures the rate of change is also continuous, with no undefined values. The text here confirms the rule. If both the base function and its partial derivative are continuous throughout our rectangle, then the theorem guarantees exactly one unique solution exists. By drawing this boundary and running these continuity checks, mathematicians create a zone of certainty. Inside that box, branching paths and unpredictable dead ends are mathematically excluded. Let's test this with a specific equation where the function is y to the power of 2/3. On the first scan, the function passes. The expression y to the 2/3 is continuous across the entire graph. But calculating the partial derivative makes the exponent negative, moving y to the denominator. This creates a division by zero error on the x-axis. Because this is undefined, The rate of change tends toward infinity along that horizontal line. If we try to draw a rectangular region that touches this red line, the theorem fails. The continuity is broken, and we can no longer guarantee a single, unique trajectory. This theorem acts as an early warning system. It shows researchers exactly where their mathematical models will lose reliability and where their predictions will fail. When you see a satellite holding a precise orbit around the Earth, you are seeing the results of mathematics successfully applied within these continuous boundaries. True predictability requires precision beyond simple starting coordinates. The existence and uniqueness theorem is the silent bedrock of applied mathematics, ensuring our equations reflect a singular reality. When an initial value problem passes these checks, it proves that within the right boundaries, the future is not a guess, it is a calculation.